In the last few lectures, we have discussed in very details the basic theory of method of partial waves and its applications, particularly to deal with the problem of scattering in quantum mechanics. In continuation of this, today we are going to see the concept of phase shift in this type of problems. Actually, you have seen that in any final result of the method of partial waves, always we encountered with a quantity which is called phase shift, denoted by the symbol delta L, which is actually called the phase shift of Lth partial wave. So it is necessary to know about this phase shift, what is this phase shift and how it can be calculated or how it can be determined. And apart from this, we will also learn about a very important theorem which is called optical theorem in very brief in this lecture. Okay. But to know about the optical theorem and phase shift, we will need the important results which we have discussed in our previous lectures. So before going to know about the optical theorem and phase shift, I have mentioned here three important results which we have learnt in the basic theory of method of partial waves. Actually, you have learnt that the scattering amplitude, which is denoted by the symbol f of theta, this is given as 1 over k summation over L 2L plus 1 times e to the power I delta times sine delta L times PL of cos theta. Okay. Here you know that this delta L refers the phase shift, which will be discussed in this today's lecture in very detail. And after that you have learned about the differential scattering cross section, and you know this differential scattering cross section, which is denoted by the symbol sigma of theta or d sigma by d omega, that is simply equal to a square of the modulus of a scattering amplitude f of theta, and so it is given like this. Okay. And finally you have seen the expression for the total scattering cross section. If you denote it by the symbol sigma, then it is given as 4 pi over k square summation over L 2L plus 1 times sine square delta L. You can see all these three equations contain the quantity delta L. So if you are talking about the method of partial waves and try to find the scattering amplitude and scattering cross section, definitely you must have a concrete idea of this phase shift delta L. That's why today we will discuss this phase shift in very detail. But before that, I am going to explain a very important theorem which is called optical theorem in very brief. What is this optical theorem? What does it refer? We will learn. You can see the expression for this scattering amplitude. This expression contains the factor e to the power I delta L. And you know e to the power I delta L, this equals cos theta plus I sine delta L. Okay. It means f of theta is a complex quantity. It will have a real part in terms of this cos theta, and it has also an imaginary part in terms of this sine delta L. Okay. So in fact, a scattering amplitude is a complex quantity. Okay. And when you will see the expression for this sigma, that is the total scattering cross section. It is a real physical quantity, not a complex. But if you are talking about the forward scattering, it means the scattering in case of which the angle of scattering theta is equal to 0. Okay. Then the forward scattering amplitude, that is f of theta equal to f of 0, that can be related to this sigma. How we can relate the total scattering cross section with the forward scattering amplitude? You can see. For this, let us first of all find the value of f of theta for theta equal to 0. You know, in general, f of theta is equal to 1 over k summation over L 2L plus 1 e to the power I delta L sine delta L times PL of cos theta. But if you will substitute 0 at the place of theta, then here at the place of cos theta there will be cos 0. Okay, so f of 0 reads like this. But you know, this PL of cos 0, it means this is PL of 1, and definitely you have an idea of Legendre polynomial. This PL of 1 is simply equal to 1 for all values of L. Okay. So f of 0 is given as 1 over k summation over L 2L plus 1 times. Now instead of e to the power I delta L, I have mentioned here cos delta L plus I sin delta L and times sin delta L times 1. Okay. Now you can see, if I will ask you what is the real part of this f of 0, which is forward scattering amplitude, then that will be 1 over k summation over L 2L plus 1 cos delta L times sin delta L. And what will be the imaginary part of this f of 0? This imaginary part will be 1 over k 2L plus summation L over L 2L plus 1 sin delta L times sin delta L, that is sin square delta L. Actually, this imaginary part of f of 0 can be easily related to this sigma, because the expression for sigma also contains sin square delta L. Okay. So let us see how we can relate this. So I have written here imaginary part of f of 0. And you have seen that this will be simply 1 over k summation over L 2L plus 1 times sin square delta L. Okay. And this expression actually holds for all real values of delta L. Why real values? Because we are trying to find the imaginary part of f of 0. Okay. Now, when you will divide this sigma, that is the total scattering cross section, by this imaginary part of f of 0, you can see the expression for sigma, that this ratio will be equal to 4 pi over k, and therefore sigma will be equal to 4 pi over k times imaginary part of f of 0. This result which we have obtained here, this is actually known as optical theorem. Why this result is called optical theorem? The reason behind this is that it was first discovered in the study of optical scattering. It means this was discovered for the scattering of light wave. Okay, and that's why this theorem is known as optical theorem. Okay. In fact, when we will study the matrix method of a scattering problem, then you will see later on in my videos, we will discuss two matrices, S matrix and T matrix. And in the discussion of that S matrix and T matrix, you will see the more generalized form of this theorem. Okay, and its physical implication will be also discussed there. But here I am not talking about those facts because I have not started to deal with the problem of matrix formulation of a scattering problem. Okay. But here we must see that when a scattering amplitude is represented as in Born approximation, you have also not learnt about Born approximation till now, but after the completion of videos on this partial wave methods, I will start to discuss the another mathematical tool to discuss the scattering problem, which is called Born approximation. Then you will see that in case of Born approximation, this optical theorem is violated. It will not remain valid. Why in Born approximation this theorem is violated? The reason behind this is that in case of forward scattering amplitude, you will see that the forward scattering amplitude is not complex, but it is real. And this theorem talks about the imaginary part of the forward scattering amplitude. That's why we simply say that this theorem, however, gets violated when a scattering amplitude is represented in Born approximation as forward scattering amplitude is real in this approximation. Okay. In fact, we will learn about this optical theorem something more as I have told you in case of matrix formulation, but till now I am not giving any more information about it. But this short concept on this optical theorem will be very helpful to you when a short answer type question will be asked in your examination regarding this optical theorem. Okay. Now, actually, the basic aim of this lecture is to discuss the concept of phase shifts. So now let us start to know what is this phase shift, how it can be and how it can be determined. Actually, you have seen that in any expression which I have mentioned earlier, in all those three expressions, this quantity delta L is present. And this delta L in the expression of a scattering cross section or in the scattering amplitude, actually this delta L is known as phase shift of the Lth partial wave. Okay. But when you say phase shift, definitely this is something change in phase or difference in phase. So let us see how this phase shift can be explained and can be determined. You know the expression for sigma. What is this sigma? You know this is total scattering cross section. This is given by the expression 4 pi over k square summation over L 2L plus 1 sine square delta L. You can see this scattering cross section strongly depends on the value of this delta L, which is called phase shift of Lth partial wave. So as the value of delta L will change, accordingly the value of cross section will also change. If you take this delta L is 0 or pi, then you know sine delta L will be 0, and that's why in this condition sigma will be also equal to 0. It means the scattering cross section will be 0 for the phase shift having value 0 or pi. But if you will take delta L equal to plus minus pi by 2 or plus minus 3 pi by 2 or plus minus 5 pi by 2, then sine square delta L you know is equal to 1. And this 1 is actually the maximum value of sine square delta L. And if sine square delta L is maximum, definitely for a given value of L, sigma will be maximum. And what will be that maximum value? Taking sine square delta L equal to 1, you can write the expression for the sigma maximum, and that will be 4 pi over k square summation over L times 2L plus 1. So if you will take L equal to, let us say, 0, then sigma max will be what? That will be equal to 4 pi over k square. Okay, but if you will take L equal to 1, then this will be actually this will be found by taking here 1, okay, 0 to 1, and 4 pi by k square plus 4 pi by k square times 3, okay, and that will be actually the sigma maximum. So for different L, sigma max will be different. For a particular L, it will have a particular value. Okay. But as I have told you that this represents something like difference in phase. So let us try to know what phase difference actually this delta L represents. In fact, in my previous video, I have talked about the asymptotic form of radial wave function several times. And you have seen that this R of R, when R tends to infinity, is given as AL over KR sine KR minus L pi by 2 plus delta L. Okay. Actually, this R of R is related to AL. Okay. R of R, this is equal to AL times JL of KR. What is this JL of KR? You know, you have studied this JL of KR several times. This is actually the spherical Bessel function. And you have learnt in very detail this spherical Bessel function, its asymptotic form too. So from this relation, by taking the asymptotic form of JL of KR, you can find the asymptotic form of R of R. Okay, actually the asymptotic form of JL of KR is 1 over KR sine KR minus L pi by 2. Okay, and this is actually the phase constant. So asymptotic form of R is defined like this. Okay, again, you know, the asymptotic form of the spherical Bessel function JL of KR, this is defined like this. Now, when you will compare these two equations, the phase of R of R, and the phase of JL of KR, what are those? Phase of JL of KR, you can see this is KR minus L pi by 2, and you have just seen that phase of this much R of R is KR minus L pi by 2 plus delta L. So obviously delta L is the phase difference between R of R and JL of KR. So in fact, this delta L is nothing, this is simply the phase difference between R of R, that is radial wave function, and this radial function. This R of R is actually the real or actual radial function, and this JL of KR is also radial function, but this is not actual. When you will multiply it by a constant like AL, then you will get it. So I have mentioned it here. You can see that thus it is obvious from 1 and 2 that delta L is the difference in phase between the actual asymptotic form of radial wave function R of R and the asymptotic form of the spherical Bessel function JL of KR in the absence of a scattering potential, that is V of R equal to 0. Okay. So this is a brief idea of delta L. But one thing is left here, how we can determine this phase shift. So now let us try to know the technique, the mathematical steps or the result by which we can determine the phase shift. For this, you must recall that R times JL of Kr satisfies the radial equation of a free particle. When you say free particle, what does it mean? A particle which is in field free region. That is, in case of free particle, you know this potential or potential energy is zero. So simply this function R times JL of Kr satisfies the radial equation. So taking V equal to 0 and at the place of radial wave function taking R times JL of Kr, you can write the radial part of the Schrodinger equation in this manner. This is d2 by dr square operated on RJL plus k square minus L times L plus 1 over R square times RJL equal RJL equal to 0. You know, here actually this k square stands for 2 mu e over h bar square. Okay. Now, we have also written the radial part of the Schrodinger equation in terms of a function VL of R in my previous video. And you know the radial wave function RL of R. If you define it like VL of R over R and you consider a potential function U of R defined by 2 mu by h bar square times V of R. If you make these two substitutions in radial part of the wave equation of Schrodinger, then we simply get that our equation becomes d2 VL by dr square plus k square minus U of R minus L times L plus 1 over R square times VL equal to 0. Okay. And after seeing these two equations, now we can do some mathematics, and after that we will be able to get the expression for the phase shift. Now let us multiply this equation 1 by VL, okay, and this equation 2 by RJL. Multiply. And after that subtract this equation 2 from 1. So when you will multiply the first equation by VL and the second equation by RJL and subtract equation 2 from 1, you will get this result. VL times d2 by dr square operated on RJL minus RJL d2 by dr square operated on VL and plus RJL times UR times VL, and that is equal to 0. In fact, here these two terms k square minus L times L plus 1 over R square, these are common in both of the equations, and so they will cancel out. Okay. Now the first two terms can be written like this. This is d dr operated on RJL dashed times VL minus RJL times VL dashed. Actually here when you say VL dashed, that means dVL by dr, and when you say RJL dashed, this is d dr operated on RJL. Okay, and this will be equal to minus RJL times U of R times VL. Okay. Now let us integrate this equation with respect to R between the limits 0 and infinity. You can see that the integral of the term in LHS, that will be with respect to R, that will be simply this much, because here there is d dr, and when we will integrate with respect to R, this dr will cancel, and the integral of differential of this much will be simply equal to this much, and limits are 0 and infinity. And in RHS there will be minus integral 0 to infinity RJL UR VL dr. Now, you know, at the lower limit, that is when R is 0, then this VL is 0, okay? And correspondingly, this VL dashed will be also 0. So this the term in LHS will vanish, it will be 0 for the lower limit. But what will be this LHS term in case of the upper limit, that is when R is infinity, then what will be this? We can find it by taking the asymptotic form of RJL, okay? So you can see I have mentioned that at R equal to 0, that is at lower limit, VL at R equal to 0 is 0. It means at the lower limit, the terms on the LHS vanish. But at R equal to infinity, that is at the upper limit, what will be the value of RJL dashed and VL dashed? You know, the asymptotic form of JL, that is when R tends to infinity, is what? This is 1 over KR times sine KR minus L pi by 2. So R times JL, this will be R times this much, R will cancel out. So the asymptotic form of R times JL will be 1 over K sine KR minus L pi by 2. Now when you will differentiate it, that is RJL dashed, what will be this? This will be K times cosine of KR minus L pi by 2 by K. This K and K will cancel out, and so this is cos KR minus L pi by 2. Okay. So this is cos KR minus L pi by 2. And similarly, this VL dashed is cos KR minus L pi by 2 plus delta L. Okay. You can also see here that the phase difference between RJL dashed and VL dashed is delta L. Now, for getting the value of the term in LHS of this equation at the upper limit, at the lower limit, you have seen that this vanishes. When you will substitute these two values in that equation, then the result becomes like this. This is sine delta L equal to minus K integral 0 to infinity RJL times UR times VL dr. This is actually the result using which we can find the value of the phase shift delta L. But after seeing this equation 5, you will find that if your aim is to obtain the value of delta L, you must have an idea of VL of R. It means if VL of R is known, only then we can evaluate the value of delta L. Okay. So now taking at first an approximate value of this VL of R for getting the value of delta L, let us see. This is an approximation. This VL of R may be taken as R times JL of KR, which is actually the radial wave function when the potential is absent. That is when there is no potential. Okay. So if you will take VL of R equal to R times JL, then this equation will become what? Here VL will be replaced by RJL. So this will be R square and JL square. Okay. So your equation is sine delta L equal to minus 1 times K integral. Instead of minus sign, I have written minus 1. 0 to infinity JL square of KR UR times R square dr. Okay. Now you can see from this equation that if the potential is real, that is this UR which you have seen, UR is defined by 2 mu over H bar square times V of R. So if this potential V of R is real, then sine delta L or delta L will be also real. So This equation shows that the phase shift delta L is real for a real potential. Again, you can see if the potential is attractive, an attractive potential has negative sign. So in that condition, you must take this V of R negative. And if V of R will be negative, U of R will be also negative. And that minus sign and this minus sign present here, when multiplied, will become plus. So in that condition, delta L will be positive. It means it is a very remarkable fact that in case of attractive potential, phase shift is positive. Phase shift is positive or greater than 0 for an attractive potential. But what will happen when the potential is repulsive? If VR is negative at repulsive, its sign will be positive. And that's why U of R will also have positive sign. And so this minus sign remain here when you will find the value of this delta L. So in that condition, delta L will be negative. So you must remember that in case of repulsive potential, phase shift is negative, and in case of attractive potential, phase shift is positive. This fact is very important for your objective type question in your examination. Okay. Now we are going to see a very important fact, that which is dependence of this delta L on the value of K. And for knowing how this delta L depends on K, we will use an approximate result, which is JL of KR equal to KR to the power L over 2L plus 1 factorial. Actually, you have an idea of this double factorial. When you say 2L plus 1 double factorial, that means this 1 times 3 times 5 times so on plus times 2L plus 1. Now, in this condition, if you consider a limiting case of KR much smaller than 1, then this sine delta L will be almost equal to delta L, and that will be equal to K to the power 2L. Okay. So in this approximation, you can see how this delta L depends on the value of K. Actually, for higher L values, phase shift decreases in accordance with this relation. Okay. But that is the case of low energy region. Okay. In fact, the partial wave method is particularly useful in case of low energy scattering. In case of high energy scattering, we talk about another method which is called Born approximation, which we will learn in our forthcoming lectures. But here I am trying to find the scattering amplitude and hence the scattering cross section by the method of partial waves, even when the scattering is not low energy scattering but high energy scattering. We can find it. How it is possible for this, let us see. In general, f of theta is equal to 1 over k summation over L 2L plus 1 e to the power I delta L times sine delta L times PL of cos theta. This is the well-known result. Now, if we make a particular approximation that this e to the power I delta L is almost equal to 1. In this approximation, you can say that e to the power I delta L times sine delta L, this will be almost equal to sine delta L. Okay. And then what will be this f of theta? F of theta will be minus 1 integral 0 to infinity summation 2L plus 1 PL of cos theta JL of KR times UR R square dr. Okay. Actually, here I have used the previous result. Okay. Now, you must remember a relation which I am mentioning here, that sine kappa r over kappa r, this equals summation over L 12 plus 1 PL of cos theta GL of KR. Here kappa, you have seen this quantity earlier. If K is the incident wave vector and K dashed is the scattered wave vector, then kappa is K minus kappa dashed. And you know that magnitude of K and K dashed both are equal. And so if theta is the incident angle, then kappa is given by 2K sine theta by 2. Okay. So when we will substitute this result, that is summation over L 12 plus 1 PL cos theta GL of KR, in this equation, that is equal to sine kappa r by kappa r, in this equation 5c, then our result becomes f of theta equal to this much. Actually, when we will learn about the Born approximation, then you will see that this is the scattering amplitude in Born approximation, and this result is valid in case of high energy scattering. Okay. So in this way, the expression for the scattering amplitude in case of partial wave analysis may be utilized even when the case is of high energy scattering. Okay. So this is all about the phase shift and the optical theorem, and I hope you have definitely understand the ideas behind this. And after this, we will learn about another important parameter of this theory, which is called a scattering length. How this scattering length is defined, what is its geometrical interpretation, all these things we will learn in our forthcoming video. Okay, thank you very much.